Hello and namaskar. Welcome back to my channel, guys. And in this video, we will go back again to the perceptron algorithm and try to understand more about it. Okay, so let's start. So, the thing is perceptron and margin maximization in linear separability. So, let's introduce some concepts. Okay, and the first concept is basically weight vector. Okay, so what is a weight vector? Let W star belongs to RD, okay, d-dimensional, that is, it is from that data sets, right? One of the point from data sets, be the weight vector such that W star transpose XI is greater than equals to some gamma for all I, okay? So weight vector is basically a vector which separates the data with some margin, okay? It's always greater than equals to some margin, right? This weight vector ensures the desired margin. What it ensures? The desired margin, how much margin it should be there, okay? There is second thing called bounding radius, okay? What is bounding radius? We define some r greater than 0 belongs to R, okay? Yani, this is from real numbers, such that for all I, the mod of xi belongs to R. That is real number. So it's less than equals to R, real number, okay? What it means, what it represents, okay? So this is the representation. Let's say we have this axis, okay? And these are points. These are my data points, okay? These all are my data points. So, and these arrows are the length associated with these data points. So these all arrows are lengths, okay? And length is norm xi, correct? So what it says that there will be a radius r, okay? What is this? A radius r which will construct a circle or let's say a boundary, okay, where all these norms, all these lengths will be less than or equals to this r, okay? So it is a boundary on all the data points, okay? For all I, norm of xi is always less than equals to r. With these parameters, okay, which these parameters, one is weight vector, second is border radius, bounding radius, okay. With these parameters, we have upper bound on the numbers of mistakes made by the perceptron learning algorithm. So with these two parameters, what we do, we can bound our number of mistakes, okay, upper bound and lower bound, okay. So we will bound the number of mistakes, that is we want, like, after certain number of mistakes our algorithm converges, okay. So the number of mistakes is nothing but r square upon gamma square. So this is basically the upper bound, okay. That is, number of mistake will be directly dependent on r square, that is the radius, okay, and the gamma square. Gamma square is basically the margin, okay. Number of mistake is directly proportional to r square and inversely proportional to gamma square. That is, if the margin is greater, the number of mistake will be less, correct? And if the radius is greater, number of mistakes will be greater. That is obvious, right? Now, with these, we have some observations. What is the observation? First observation is the quality of the solution depend on this margin gamma. Yes, right? This depends on this gamma, correct? Second is the number of mistake is influenced by the margin associated with W star. Okay. So whatever the weight vector we have, margin associated with this, because we have this. Okay. So margin is somewhere the weight vector ensure the desired margins. Okay. And third is the weight vector, that is W of perceptron, need not to be identical to W star. Okay. It means that there may be many W stars. Okay. Just like if you see in this picture. So we have one W star here. Okay. there might be some other W star as well, which separates our data set. So if we talk about in this context, okay, so this is our plane and this is our W star 2, let's say W star 2, due to which we get this margin, okay, this margin, correct? And it separates these data points and these data points, okay? These margins separates this blue one, okay? Now, at the same place, we can have another W star, okay? Basically, W star determines what? The margin, right? So, we can have another W star which gives this margin, and this margin as well separates this both data sets, correct? This margin also separates these both data sets, right? You see? So, we have two margins, right? And you can see this margin is more and this margin is less, right? So, there may be many margin. So, what we want? We want the margin to be maximum, right? That is our desire. So, goal is basically what? Margin maximization. A single data set can have multiple linear classifiers with varying margins as depicted in the picture. As I shown in this picture, that I can have multiple W stars for which I can have multiple margins, right? Now, our goal is to maximize this margin. To formalize our objective, we aim to maximize the margin gamma. Okay, so we say this margin as gamma, correct? And our goal is to maximize this. That is, if we write it in mathematical way, it will be maximize W and gamma of gamma. Okay, so basically, given two parameters W and gamma, we want to maximize the gamma such that W transpose xi yi should be greater than equals to gamma for all I, and norm should be equals to. Okay, so this is my mathematical formulation of our desired goal, that what we want to achieve this. Okay, to simplify our objective, that this is like little bit hectic to understand, so let's simplify it. Okay, so we want to express gamma in terms of width W. Okay, W is our width. We just making a new parameter width W. Okay, so we can write this as this thing, that is maximize max of W, okay, of width W such that W transpose xi yi is greater than 1. Okay, so we included this here and we said formally this. Basically, we have two parameters here. Now we can say that we have one parameter, and you know, if I have one parameter, and you know that this is nothing but a constraint optimization problem. So we can solve that and can get a W, okay, which gives us maximum margin. Okay. Now, so we said that max W of width W, right? So what is this width? Width kya hai? What is this width? So let's understand that what is this width so that we can maximize it, right? So what is this width? So let's say these are this is our plane and these are our data points. Okay. So and this is our boundary. If we say we take this point and this point, this will be the margin. That is that what we want, like the maximum margin we want. Okay. So this is our margin. Correct. Let's say this point is x and this point is z. And for this W transpose x is, let's say, -1 because this is considered as -1, and W transpose z is 1. Basically, the point is z and here point is z. So this, correct? And this is x1 point and this is x2 point. So distance will be same all the places. So whether I say this or this or this, everywhere the width is equal because these are basically two parallel lines. Okay, so this is width. This gap is width. So width W, we can say that it is nothing but the distance between these 2 points. Correct? Two parallel margins. This is the distance between that two parallel margins. Let x1, x2 be 2 points on the margin and opposite side of the decision boundary. So this is our decision boundary. Okay, this side all points are -1 and this side all points are +1. Okay, so we say that, let's say x1 and x2, okay, x1 and x2 be 2 points on the margin, on that particular margin, this margin, right? And opposite sides of the decision boundary, both are opposite sides. So we take 1 point from this boundary and 1 point from this boundary, and the distance between these are basically the width. Then the width is given by x1 transpose w minus x2 transpose w will be equals to 2. Okay, so this is basically we say this is basically w of 1 and this is basically w of 1. So whole this distance will be 2, correct? So we say x1 transpose w minus x2 transpose w will be equals to 2. From here we can take common x1 x2 transpose w equals to 2. Okay, and we know that this is x transpose w, we can write it as x when we take the norm. Okay, basically this is our dot product. So x1 x2 norm w norm cos theta equals to 2, and from here we can it will be like theta is 0, so it will be 1, and we will get x1 minus x2, that is the distance, that is the width, is equals to basically 2 upon w. Okay, so this is our width, so we have to maximize this. Okay, so max of w of 2 upon w, this is what we want to maximize given the constraint. Hence our objective function can be restated as maximize w of this such that this is given constraint. Okay, this is our constraint. Now we can frame it as maximization problem, or well, this is already a maximization problem. So we can frame it as a minimization problem as well, and we can write it as maximize this will be equals to minimize this of, and we will reverse this. Okay, so minimize w of 1 by 2 of norm w. Okay, such that this is our constraint. Okay, so we have already learned that we can do this, right? The constraint optimization problem we have already discussed. Okay, so in summary, if I summarize all these, then finding the separating hyperplane with the maximum margin is equivalent to finding the one with the smallest possible norm vector down, right? So our goal was to maximize this. So it is equivalent to saying that finding the one with smallest possible norm vector w, that margin which has smallest, that hyperplane which has smallest norm vector w. Okay, now we will recall our constant optimization problem again. Okay, so that we can solve this problem. So when we have problem like constant optimization like this, okay, min of fw such that gw less than equals to 1, this is a statement. If we have this, okay, then we solve this using Lagrange function. Okay, what is this Lagrange function? Lagrange function Lw comma alpha is equals to f of w plus alpha transpose g of w for all I and alpha greater than equals to 1. So this is our Lagrange function which we used to basically solve the constraint optimization problem earlier. We have done this in MLF course, right? So now we can write this problem as Lagrange function, this, right? I am just talking about general form. Okay, you don't like feel that from where it can. We are just taking this and we are doing some basically we are revisiting to this constraint optimization problem. Okay, how to solve that, we are looking this here, and then when we reach to the conclusion, we will then apply this to our problem to solve that, to get the optimal w. Okay, so maximizing the Lagrange function with respect to alpha. Okay, we want to maximize this with respect to alpha first. So we can write this as maximize alpha greater than equals to 0 of Lagrange function will be equals to maximize alpha greater than equals to 0 of fw plus alpha transpose zw, correct? And from this we can say we have this conclusion that if g of w is greater than 0, okay, if g of w is greater than 0, it will be infinity, value will be infinity. And if g of w is less than 0, we have value as f of w, okay, whatever the value of f at w, we have this if g of w is less than equals to 0. If g of w is greater than 0, then we have the value as infinity, okay. In the picture, it's right, like we have this boundary of g of w less than equals to 0. Now, if there is a w from this point, we will get it as function value, okay. But if our point is outside this region, this g of w less than equals to 0 region, if we have point outside this, okay, we will get the value as 0. Sorry, infinity, okay. Since the Lagrange function is equivalent to f of w when g of w is less than equals to 0, we can rewrite the original problem, that is this problem, as min of fw, because we know that, right, this maximizing this, what it means that we can write this function as the value of this. So the idea will be minimize w of fw will be equals to minimize w given minimize w into maximize alpha greater than 0 of Lagrange function, right, this function, because we want to get that w, okay. So we want to minimize w, so minimizing w of fw will be equals to saying that minimize w of maximize alpha greater than equals to 0 of Lagrange function, okay. That is also if we put the value of this, we can write minimize w max of alpha greater than 0 f of w plus alpha transpose gw, okay. So here what we did, here we maximize with respect to alpha, right. Now here what we are doing, we are minimizing with respect to w, because we ultimate goal is to find the w. In a general, interchanging the position of the min max function, okay, interchanging these position is not permissible, okay. So in general we can't do this, like saying this, that minimize w of maximizing alpha equals to 0 of this function is equivalent to saying that maximize of alpha greater than equals to 0 of minimizing w of this function. We can't say this in general, okay, until or unless all involved function are convex, or we can say a nice function. If we have a nice function that is convex function, then only we can do this transformation, that rearrangement, that saying min over max is equivalent to saying max over min problem, okay. So we can't do this until we have the nice function, that is the convex function, okay. In our case, both f and g, both the function f and g are convex function, which allows us to do this, that min over max problem we can convert it into max over min problem, okay. So that is minimize w over maximize alpha greater than equals to 0 of this is equivalent of saying maximize alpha greater than 0 of minimize this function, okay. Now we have this, and we know this how to solve this problem, right. We have m constant denoted as gi of, and let's say this is one problem, okay. When we have two functions, let's say we have multiple constant. In this case, we had one constant, right? G of w less than equals to 0. If we have multiple constant, then we can write it as, if we have m constant denoted as gi of w less than equals to 0 for all I belongs to 1 to m, then we can write this as min w over fw is equals to min of w over max alpha greater than equals to 0 of fw plus sum of I to m of all alpha I gi of wi for all I. Okay, we can do this for multiple constants, right? That is equivalent of saying that we can interchange these, right? So max of alpha greater than 0 over min of w of this function. This is our multiple constant, okay? Multiple constant optimization problem. Now from here we will do one more thing, that is formulating the dual problem. Okay, so we got this problem, right? We got this solution. Now we will formulate our problem. So objective function is basically to minimize this given this, correct? This was our original problem, right? If you see, okay, so we are now working on this and formulating the dual problem, that is the constant optimization problem, min over max and max over min. Okay, so objective is to minimize this. Okay, here constraint is basically this, correct? And we can write it as 1 minus this, and whole this is basically nothing but g of w. So we got the ideal problem, that constant optimization problem with g of w less than equals to 0, right? Now, if we have this, we can introduce the Lagrange function, right? We can write this Lagrange function, right? We have g of w, we have f of w, right? So we can write the Lagrange function. So when we write the Lagrange function for Lagrange multiplier alpha, because we have introduced a alpha I r, right? Okay, here you can see this is basically a Lagrange multiplier. Okay, so we can introduce this with alpha belongs to Rd. So we can write our Lagrange function as this. This is f of w plus g of w, and it is multi constant, right? So we can write as this. Now, as both are convex functions, we can use that duality problem principle, and we can write it as min of w over max of alpha greater than equals to 0 of this problem is equivalent of saying max of alpha greater than 0 min of w given this function. Okay, we can do this. Now, if we talk about this minimization w, okay, so this we know how to solve. That is, for any alpha greater than 0, for any alpha greater than 0, we have this minimize w of this. Basically, I wrote this function here. Okay, and for any alpha greater than 0, the solution will be nothing but it will give a w star alpha, okay, plus summation of this will be equals to 0. Because we know minimizing this. For minimizing this, we will take the gradient and we do the gradient equals to 0. And this is the gradient we get, okay. And from here, we can write that w star alpha is equals to sum over I equals to 1 to n alpha I, and basically we found the gradient of this as this, okay, w transpose xi with respect to w will be minus xi and wi will be there only, okay. So it is it will come here, so it is minus. So if we take all these points other side the equals to, it will give me this, and this is nothing but sum over I equals to 1 to n alpha I xi yi, okay. Now here note something, alpha is basically greater than equals to 0 as we have taken, right, for all any alpha greater than equals to 0. Now this xi is nothing but all the data points belongs to Rd, and this is nothing but plus 1 minus 1, correct? So this alpha star has a nice form like this, correct? Now this also leads us to a vector form, vectorized form of the solution, that is w star alpha can be written as vectorized form, and that is w star alpha equals to x y alpha if we consider all this, right? Where x is belonging to R d cross n vector, y belongs to R n cross n vector, and alpha belongs to R. Okay, we know this. Now, so when we got this from we have solved this. Now let's rewrite it. Okay, so rewriting it, maximize alpha greater than equals to 0 of this function, that is duality problem, right? We get maximize alpha greater than equals to 0. This will we can write as this, and this we can write as this, basically multiplied alpha inside. Now maximize, so we can take the gradient, okay, and we know that the value of w, right? We got the value of w, so we will put here. maximization problem, because we have what? Min, max over min, right? So from min we solved and we get a W, right? We put it here, and we get W equals to this. So W transpose W is basically this transpose this minus alpha sum over alpha I, and basically this is and we can write W as this, and this already we have. Okay. Now, so we got this and this. So it is 1.5. So it will be minus 1/2. And this we already have. So we got this. Okay. Now observe it. So we will do some observation on this. This is basically our solution, which will give optimal alpha also, optimal W also, right? Now let's do some observation, and the observation is first on dual and primal variables. Okay. And the observation is the dual problem is characterized by alpha greater than equals to 0, as you can see here in Rn, and problem primal problem deals with W in Rd. So this is our primal problem solution, right? And primal problem deals with W star, while the dual problem, which this deals with alpha star greater than 0, right? Second is the simplicity of dual problem. That is, solving the dual problem is often considered easier as compared to primal problem. Okay, so solving the dual problem is easier than the primal problem. And third thing is basically the dual problem dependence on X transpose X. You can see. Yes, you can see this. X transpose, if we multiply this, we will get this X transpose X. That opens the door for kernelization technique. So we can, when we get this X transpose X there, we can kernelize it. Okay. So we examined this dual problem and we got these much things that yes, we can do this. So basically when you write it like X transpose, Y transpose, alpha, X, Y, Z. So we get X transpose X, right? So these all things, alpha transpose, Y transpose, X transpose, X, Y, alpha. So we got this X transpose X, that is the dot product. And when we got this, we can kernelize it, okay? So that's why we can use the kernelization techniques to make it more optimized, right? Now let's optimize this, our primal problem. So here in interpreting the W star, okay, the optimal W star emerges as the linear combination of data points. You can see here we have data points, here we have summation, and it is nothing but linear combinations, right? So W star emerges as the linear combination of the data points, where each data point significance is determined by the corresponding Lagrange multiplier. Okay, so each data point signifies what? The significance is determined by each point significance is determined by this Lagrange multiplier alpha. Okay, that is cool. Second thing is verifying varying importance. Okay, that is consequently some data points exert greater influence on W star with than others. Okay, so there will be some data points which will make the greater influence, okay, on this W star than some other data point. Okay, so these two are the observation, the interpretation of this point. Okay, now we will revisiting to the Lagrange function, which was this. This is our primal problem, and that is equivalent to saying that dual problem. Okay, so we have this too, where W star is the solution of obviously primal, and alpha star is the solution of dual problem. Okay, so putting the W star in the primal problem, we get this, right? That is here W star, here W star, we get this. And putting alpha star here in dual problem, we get this. Now we know that G of W star is always less than equals to 0. That means maximizing over this, we can write it as f of w star, as like we know that this, right? And we have seen that if it is greater than equals to 0, we have value as infinity. If it is less than equals to 0, we have function value, right? So this will be equals to this function value. And this minimization problem is this. Now, the minimization problem will give the solution as this. When we put what we did, we put the w star at the place of w. Okay, so we will get this. That will be always less than equals to 0 because we have to minimize it, right? So it will always less than equals to 0. And this two terms are same, so it get cancel out. Okay, so we get this less than equals to 0. That is this. Correct? We get this constant. However, considering the constraint where alpha star is greater than 0 and gs of w star is less than 0, we have this, right? We already given the constant alpha is greater than equals to 0. We have this less than equals to 0. So we will always give the product as less than equals to 0 because this is greater, this is less. So plus into minus is always minus. That is always less than equals to 0. But we have this which is greater than equals to 0. So these two can be possible only if this is not less than, not greater than, but equals to 0. Both this constant will be true if we have the condition of this. Correct? And writing it for multiple constraint, we can write it as this alpha I star. Basically, we are including all those I given. So we have this, right? Means, what it means? Means either one of these will be 0. Either alpha star will be 0 or this will be 0 because the product is 0, right? So let's consider that g of w star I is equals to 0. That is the constant is 0. So if I say g of w star is 0, that is equivalent saying g of w star is basically what? This function, and that is equals to 0. That is alpha star 1 minus w transpose this equals to 0. Right? Importantly, when alpha is greater than 0, we deduce that w transpose xi yi is equals to 1. Okay? If alpha star is greater than 0, we get this. Correct? Because this is greater than 0, so it's important that it will be 0 and this will be 0, which gives us this. Correct? Now, this implies that this thing implies that ith data point resides on the supporting hyperplane and significantly contributes to the determination of W star. That means what we say W transpose xi yi. Basically, this is nothing but g of z, and it is equals to what? It means that all these xi, right? All these xi are those points which are on this hyperplanes. And these are the points which signify the W transpose. W, this W. No other points, but only these points which are on this hyperplane, right? And these is called supporting hyperplane and signifies contribution to the determining of W star. Okay. Consequently, the data points with alpha I greater than 0 earn the title supporting vectors. Okay. And this algorithm is known as support vector machine. That is, for signifying the basically for determining the W, okay, the optimal W, we only need those data points which are on this hyperplane, these hyperplanes. Okay, so we can throw all the other data points which are not this hyperplane. Okay, so for all alpha greater than 0, we get that W which is on this hyperplane. Okay, we need only those for determining the W star. And this And these are called basically these vectors, these vector points are called support vectors. Okay, and this algorithm is called support vector machine. So let's talk about support vector machine. Support vector machine is termed as the category of supervised learning algorithm designed for classification and regression analysis. Okay, SVM aims to identify the optimal hyperplane that maximizes the margin between the different points from different classes. Okay, what it does, it maximizes the margin. It gives us the W with the maximum margin. In scenarios where data is non-linearly separable, okay, where data is not linearly separable, the SVM employ kernel function to map the data into higher dimension space with a linear decision boundary can effectively segregate the classes. If we have, let's say, non-linear data, okay, non-linearly separable data, then we can use the kernelized version to basically uh, project it into higher dimension, okay, and then from there it can define a linear decision boundary and can effectively categorize the classes, basically separate the classes. Insights. Here, W star represents a sparse linear combination of data points. So basically, some data points which are on the vector supporting vectors. W star is nothing but the linear combination of all these. There are two types of SVM algorithm. One is hard margin SVM algorithm, and there is a soft margin SVM algorithm. So hard margin SVM algorithm is basically applicable only when the data set is linearly separable with a margin parameter gamma greater than equals to 0. Okay, if data set is linearly separable, we can apply the hard margin SVM. Okay, its key step involve direct or kernelized calculation of Q. So first we will calculate the X transpose X, basically whether you use kernelized function or directly do this, it's your choice. First compute that matrix Q, that is X transpose X, then gradient descent. Okay, so then employ the gradient descent for dual problem to reach the optimal W, that is this. Okay, and I have told you that this Q is nothing but X transpose X. So these are all those points, and Y equals to 1 is here. Okay, in the gradient descent algorithm, to iteratively find a satisfactory set of Lagrange multiplier alpha, initialize alpha as 0 vector in Rn. Okay, so when we do iteration, so this is basically iterative step of gradient descent. Okay, so first initialize alpha as 0 to get all the optimal alphas, okay, alpha stars. Now after this, we will reach to a optimal W, right? Then do the prediction. And prediction for non-kernelized version is basically label of X test we want to predict, right? It is nothing but sign of W transpose X test, where we will get the W from this gradient descent step will do above. That is this, okay? Xi transpose X test, sign of this. For kernelized SVM, this was for non-kernelized SVM. For kernelized SVM, we will do label of X test equal to sign of W transpose kernel function of X test. Okay, that is this. Correct? And this way we will predict the labels using the SVM algorithm. Okay. There is soft margin SVM also, which will be used to accommodate some misclassification in the training data set. Okay. So it basically extends the standard SVM algorithm to accommodate the misclassification in the training data set. Okay. This extension is particularly useful when dealing with non-linearly separable data set, because the misclassification will be there. And to tackle that, we can use the soft margin algorithm. Okay, it is introduced a regularization parameter to control the balance between maximizing the margin and allowing for misclassification. So what we do, we have this the primal formulation for this extension can be minimize of this right? Plus this, such that we have this constraint, okay, where this epsilon I is greater than or equals to 0. Okay, here C, this C serves as the hyperparameter governing the trade-off between the maximizing the margin and minimizing the classification. So basically, I said as we will introduce a regularizer parameter C. So this is our regularizer parameter, okay, and this is nothing but epsilon. No, that is equals to this, right? Such that we have this constraint for all this greater than equals to 0, all the norm greater than equals to 0. And this is basically the hyperparameter, okay, which regularize the balance between maximizing the margin and at the same time allowing the misclassification as well. The additional variable epsilon I represents the adjustment needed to satisfy the constraint. So this is basically the that adjustment, how much adjustment we need. Basically, you have seen that those regularization method, right? Where we use the regularization parameter to basically regularize the misclassification or approaching to 0, right? So here also that thing is this thing is doing the same thing, okay? And this was the pretty much it for the SVM algorithm. I hope you understand all this stuff. And if you want this PDF, okay, you can check my LinkedIn. I will soon post with all these PDFs and all. Okay. So if you like the video, please like it and subscribe the channel. We are nearby to 5,000 subscribers. So thank you for watching. We will see you next time.